Before I start solving the exercise, I would like just to prove something here that we're going to use in the exercise. We know that the magnitude of any force is equal to radical its x component squared plus its y component squared. So if the force was a horizontal force, then its y component is 0. And thus F is equal to radical of x squared plus 0 squared here. 0 squared is 0. So we will be left with F equal radical of x squared, and this will come out as Fx. So that's why if you're given the magnitude of a horizontal force, we can consider that its x component, the value of its, or the magnitude of its x component, is equal to the magnitude of the force, and the magnitude of the y component is 0. However, if the force was a vertical one, then at the x component, its x component is 0, and thus, by the same way, we can prove that the magnitude of the force is equal to its y component. Now, moving to this exercise, we have a sphere of mass m is suspended from a light spring. The sphere is pulled aside by horizontal force F of magnitude F equals 2 Newton. The sphere maintains equilibrium where it makes an angle alpha equal 45 degrees with respect to the vertical. Take g equal 10 meters per second square. Name and represent the forces acting on the sphere. When you are asked to name, you have to say the horizontal force because they called it so. And you have to give the symbol between parentheses F vector. Then write weight W vector, then tension T vector. Now, what about representing these forces? If you were given the magnitude of each one of them, then you have to take a scale and then calculate the length of each vector and then represent it. However, this is not available now because you are only given the magnitude of the horizontal force F, but you're not given the mass, so you cannot till now find the magnitude of the weight, and also not given the magnitude of the tension force. So we are going to represent the forces without a scale, which means that you won't be evaluated for the length of the vector, but the points or the objectives are to be able to represent the force from the correct point of application. The line of action must be correct, and the direction plus name the vector. And for example here, you know that the weight is a force acting at a distance, so you should represent it from the center of gravity of the object. If you did not do so, then it's going to be considered wrong. So then you draw vertically at whatever length, but يكون logical, not, and do not exaggerate. And name the W vector, name the center of gravity G, for example. And as for the tension, you know that it's always along the elastic body. In this case, it's the string. So you draw it starting from the point of contact between the string and the object, along the string, upwards in this case, and you have to name it T vector, while point B, point of contact between them, is already named. And that's it for this part. Now concerning the second part, determine by applying the equilibrium condition, the tension in the string and the mass of the sphere. If you want just to make a comparison between this one and the exercise about the girl Layan who was swinging on a swing and was at equilibrium position at a certain time. In that case here, we were given the magnitude of F and the weight, and then we said because they are perpendicular forces, so the sum of these two forces is equal to the diagonal. And then we found T prime, the magnitude of T prime by Pythagorean, and related it to T. And we were not given theta here. However, in the current one, in the exercise we're solving right now, the opposite is true. We're given the angle between the string and the vertical line, but we are not given the weight. So we cannot say, start by saying, F plus W equal diagonal. We cannot find the magnitude of the diagonal because W is unknown. So we shall think about a second way or another way that could help. The most general one is by finding the x and y component, or finding the expression at least of each x and y component, then apply the equilibrium condition along x-axis and along y-axis, or for x components and for the y components. So starting with F that is given, the horizontal force, because it's horizontal force, so Fx is equal to the magnitude of the force, which is 2 Newton, and Fy equals 0 Newton. And W is equal to Wx. Wx is 0 Newton because it's a vertical force. And Wy should be equal to W, the magnitude of W. It's equal to m times g. So for the weight here, we cannot find the value, the magnitude, but we can at least express it in terms of other terms that we are going to deal with later on. So g is given, we still need to find m in a way or another. And we have t vector, command x and y component. So if you project t on the x-axis and on the y-axis, we have these two vertical lines are parallel to each other, and this is bisecting them. So these are corresponding angles. We can consider this angle to be alpha 2 because, as you can see, the f here, these are corresponding angles of parallel lines are equal. So this is 45 degree. Now, in order to determine whether we have to use the sine or the cosine when finding the components, we have to check the triangle. What is facing alpha? What is the component facing alpha? Is it tx or ty? So it's tx. That's why, because tx is facing alpha in this case, it's facing the given angle, so we have to use sine, because sine alpha is equal to opposite over hypotenuse. Opposite is tx and the hypotenuse is t. So tx is equal to sine alpha. So if tx is t sine alpha, then definitely ty is t cosine alpha. Or again, we can check it here and look what is adjacent to alpha. It is ty. This is ty. It's opposite, and these opposite sides are equal and parallel. So I can consider this one to be also ty. So cosine alpha equal adjacent over hypotenuse. So it's equal. So ty is equal to cosine alpha. Now I have the expressions. I have to go and apply the equilibrium condition and figure out what's going to happen. So let's start with the horizontal components. Let's start by applying the equilibrium condition for the x components. I named it here external just to differentiate it between it and the given horizontal force. So by this one here external, I mean the total. Okay, that the sum of all the external forces. It's equal to 0. Here I no more use vector. When I start talking about x component alone and y component alone, I no more write a vector above f and 0. So let's start. Plus fx, we have to check is fx positive or negative. It's in the positive direction. So we take here this the positive and this the positive for x. So upward the positive for the y direction, and to the right is the positive direction. This is considered by convention. So now fx or f is in the positive sense. That's why I write plus. And wx is 0, so it doesn't differ with where I write plus wx or minus wx. And then tx is in the negative direction. That's why I have to write minus tx equal to 0. Substitute 2 Newton plus 0 Newton minus tx equals 0. Now I have tx equal to Newton. But I'm looking for the magnitude of the tension. I'm looking for t, not for its x component. Let's try to relate things to each other. So tx, is it related to t in a way or another? Yes, it is, according to this formula. So tx is equal to t sine alpha. Then t is tx over sine alpha. Then it's 2 Newton over sine 45. And then t is equal to 2.8 Newton. So 2a is done. Now we still have to find the mass of the sphere. The mass of the sphere was found to be related to W, which is in the y direction. So let's go and apply the equilibrium condition in the y direction. Again, sum of all the external forces in the y direction is equal to 0. The sum of the magnitudes of all the external forces equal to 0. So Fy is 0 minus Wy, because Wy is in the negative direction. That's why we write minus. And Ty is in the positive direction, so we write a plus Ty equals 0 Newton. 0 minus mg plus t cosine alpha equals 0 Newton. Substitute g is given 10 minus 10 m plus 2.8 cosine 45. We can now use the value of t obtained in the previous part. Equals 0, so we're looking for m, divide by, move 10m to the other side, it becomes a plus, and then divide by 10 both sides, so the mass is 0.197 kilograms.